for example, if we're getting started here, one of the themes that we had earlier was there's two reasons why something will not bond. Okay, one is surface contamination, and the other is surface roughness. Okay, and so all the joining processes have to worry about how do you overcome those two barriers to joining. Now, in many cases, well, in cold welding, how do we get rid of surface contamination?
Use a shear or an angle.
You use a shear, some type of shearing, and you try to push the material out of the way, right? So, surface roughness, we basically use lots of pressure. That same shearing, basically the shearing action, both tries to move the material out of the joint, and we also try to break down those surface asperities and get metal-metal contact. And then one of the reasons you have to do that is it takes too long to just break things apart and put them back together if you could. It turns out this is a book, it's a 2-volume set written by a company in Webster, New York that makes a lot of machines, a lot of things that make copies of things. So we won't mention the company yet. But it says there's chemistry and physics of solid adhesion. When a plate of gold shall be bonded with a plate of silver, this is from 1250 AD, with a plate of silver adjoined thereto, it is necessary to beware of three things, of dust, of wind, and of moisture. For if any come between the gold and silver, they may not be joined together. So that's surface contamination, okay? Just stated a little bit differently. Now this is chapter 1 of the first volume, and what I like to do with this is the introduction, chemistry and physics. He talks about the 4 forces of nature. Anybody taken physics before? You know what the 4 forces of nature are? There's the gravity force, electromagnetism, the weak interaction force, and the strong force. We're getting here to Richard Feynman and quarks and things like that. The weak force exists over less than 10 to the minus 16 centimeters. The strong force over less than 10 to the minus 13 centimeters. So these are gluons and intermediate bosons. And gravity tends to work over fairly large distances. And this is a book on adhesion, right? So that's about what this book is worth. Okay? Now I have to retrieve it from the trash can because I have to use it again. Catch this book is in the trash can a number of times later as I give this lecture. But that's going back a little bit too far into the fundamental physics. Okay? We don't need to go back and talk about how nuclei are bound together. This guy does, but that's kind of pseudoscience. There are some good things in here, however, and we're going to talk about the 2 primary forms of what I call adhesive bonding, and this is kind of my little way of looking at it. But I call them type 1 and type 2 for adhesive bonding. Type 1 adhesive bonding is essentially wetting of a liquid between 2 surfaces. And this is explained, you've got a handout, this comes from one of your handouts, and it's chapter 3 of this book. This is the 2nd edition of the Handbook of Adhesives. There's a 3rd edition which doesn't have the same chapter 3. You guys should be pleased to know that the guy who wrote chapter 3, Zisman, used to be at the Naval Research Lab for years and years and years. Okay, so somehow, for some reason, the U.S. Navy was interested in adhesion. Okay, they had a guy who made a specialty at it for years and years. And so he talks about elastic deformation, plastic flow at the asperities, and later in here he'll talk about contamination. Now, one of the things about adhesive bonding that makes it different from virtually everything else we're going to talk about in this course is the fact that in adhesive bonding, you don't get rid of the contamination. You just bury it beneath the surface. Okay? All the others, soldering, brazing, diffusion bonding, cold welding, and fusion welding, which half this course actually, about half the course, deals with fusion welding eventually, which is what you guys probably thought this course was all about. But the first half is soldering and brazing and cold welding and stuff. Those other processes actually get rid of the surface contamination. And then many of those, soldering, brazing, and fusion welding, use a liquid between the surfaces to take care of the surface roughness. Adhesive bonding uses a liquid, generally between the surfaces, at least some form of a liquid, to take care of the surface roughness, but it doesn't get rid of the surface contamination. And because it doesn't get rid of the surface contamination, adhesive bonding never has the strength of a solder joint or a braze joint or a weld. Okay? Inherently, because it just buries the contamination, you're dealing with weaker bonds. You're not dealing with primary bonds on the surface, the strong primary bonds. You're starting with van der Waals bonds, and therefore your joints are always going to be weaker. Now, if you have lots of surface area, that's not going to matter as much. But in fact, we all know, all of us with children who had a child bring a little plastic part to us that they broke on a toy and said, "Mommy or Daddy, can you glue this back together for me?" And you try to glue two things like that broke on the plastic, and it never holds, right? You can't do it because it's adhesive bonding and you don't have enough surface area. Now, if you've got lots of surface area, like I cut my finger and I put a Band-Aid because it's pouring blood out this morning, lots of surface area on that Band-Aid, and it will stick. Now, it's not as strong as if I actually welded with crazy glue, which is a little bit stronger, and you actually can weld your fingers together if you get an arc flash of sufficient intensity and it starts melting your skin together. Anybody ever seen that? Some people, electricians who are not doing things properly sometimes end up coming out with webbed hands. Seriously. I mean, people who've gotten an arc flash, you actually can melt your skin together. Okay? So make a real weld with human skin. It's mostly water anyway. You just kind of, we're going to find this, well, and actually it's more welding. Anyway, this is wetting of liquids. If I have a solid adherent and an adhesive in between, and I have a liquid that wets the surface, and we'll go through the math here in a second, I can bond two things together. Now, any of you ever worked in a machine shop? You know what Johansson's blocks are? Joe blocks or Weber blocks? Sometimes they're called. I'm going to be smart enough to look this up. Johansson blocks are these are Weber blocks made by Starrett, which is a company that makes tools like, well, lots of fancy tools, machinist tools. But if I'm trying to do something really, really precise, this is a 3-inch, these are two 3-inch Johansson blocks. And the ends of these are ground very, very precise. And I have a calibration traceable to the National Bureau of Standards that says these are 3 inches plus or minus 50 millionths of an inch at 70 degrees centigrade, or not 70 degrees Fahrenheit, or maybe 72, whatever it is. I can look at the calibration. But if I put them together, they will stick together. Okay? And it takes a little bit of force. You actually ring these together. They call it ringing together. You have to slide them together. There's a thin film of oil on the surface, and that oil is the liquid that's causing the bonding. Okay, surface tension is holding that together. They'll come apart easily. Try not to ding the edges. Those are actually chromium carbide. Here's the lubricant, just a little petroleum distillate, which you also have to put on and keep. Those won't rust as easily. The steel ones will rust. If anybody wants to see the certification, traceable to the National Bureau of Standards, June 28, 1996, NIST test number, and it gives you all the calibration standards back here for these things. And so if you're trying to machine something very precisely, down within a few tenths of thousandths of an inch, okay, because that's 50 millionths, okay, that's quadruple 05, okay, accuracy at 72 degrees Fahrenheit or whatever the temperature is. And it's basically the liquid, and in fact that's got a little bit too much liquid. Typically a machinist will take a clean cloth, wipe off any of the oil, and then they use a little bit of hand oil, okay? And they just kind of rub their hand on it to get a thin layer of oil, to get it nice and thin, and you can stack those up with that type of precision, and you can put it on your milling machine, and you can measure a dimension in the same cutting fluid that everything else is being machined in. So even if the temperature is not 72, you're measuring a material with a similar coefficient of expansion to what you're machining if it's steel. And if everything's 80 degrees or everything's 70 degrees, you're getting an accurate measurement. Okay, so that's the way you machine things to very high precision. But in fact, there is a bonding just because the liquid surface tension wants to pull these two together. You see the wetted surface here, and in fact, if you would just put a big bubble of this stuff here, and it wants to wet things together, it would pull it together. If you've ever seen, if you took a bunch of small ball bearings and you put a wetting liquid on there, and the ball bearings just spread out a little bit, it causes them to pull in and suck up together. Okay, the liquid actually has an adhesive attractive force. And it turns out the surface energy of all that, or the formula for surface energy, says that if I take my thing here, I can calculate the pressure here, and the difference in pressure is equal to the surface energy times the curvature, which we usually have as kappa. So this is surface energy. We talked about what causes surface energy, unsatisfied bonds, and this is curvature. And I don't know if you remember, but we can talk about pressure in the liquid, which is the adhesive, minus the pressure in the surrounding air is going to be the surface energy between the liquid and the vapor, which is this surface. So here's your liquid, here's your vapor. And it's this surface energy here that's pulling these things together, and that's going to be equal to the curvature is 1 over big R minus 1 over little r, where big R is the radius of these. If these are two circular discs, 2r, and D is equal to approximately 2 little r. Okay? So I've got a radius of curvature here, and I've got some radius of curvature here. Now, if this is a flat surface, 1 over infinity is 0, and it doesn't matter, this little r is very, very small. And that little r is basically the thickness, or 2 times the thickness of that joint. And you end up with a pressure in the liquid minus the pressure in the air is minus gamma over r. And maybe it's minus gamma over 2r, doesn't really matter. But it's also negative. So there is a negative pressure within that adhesive. If it wasn't a liquid, if that was a soap bubble, it would shrink down to 0. Okay? But it's a condensed phase, it's a liquid, can't shrink anymore, and it stays there as the adhesive. Okay? Now, there are a number of different types of adhesive that we use that work this way. Most of the adhesives that work this way happen to be things where the adhesive does not dissolve or interact with a rough surface on the adherent. Okay? Because type 2 adhesive bonding, which actually turns out to be much more prevalent, is just simple mechanical interlocking. People, how far the joke walks, and people try taking them apart and putting them back together. If they get too dirty, they won't work. In fact, if I do it now with chalk on my hands, the chalk dust thickens the joint too much, and they won't work. Those are extremely flat, extremely parallel surfaces within 50 millionths of an inch. So it doesn't work if you have a very rough surface. Yeah?
Why did you say 5/10,000 instead of 50 millions?
It's not 5/10,000. That's, oops, I said, that's supposed to be quadruple of 4. Okay. I left a 0 out. That's 50 millions. Okay. Sorry. I did say quadruple of. I didn't write it, right? So I'd say 5/10,000, but 5/10,000 is 500 millions.
Right.
Okay. So it's 50.
Or
50
500,000. 50 million sounds a little more impressive than 5.
That's right.
5,000.
It does, doesn't it? And it turns out when you start getting to that, those types of numbers, you're getting to over a 3-inch distance. You're getting to 1 part in what, 100,000, or 2 parts in 100,000 in manufacturing. Typical manufacturing tolerance. I don't know if you guys get lectures anymore from Dan Whitney, but Dan Whitney taught me this. He's a lecturer in mechanical engineering. He used to work at Draper Lab, and he used to do a lot of work with the Navy on manufacturing and shipbuilding. Back when the Navy used to build ships, or build more ships, or whatever the story is. But he pointed out to me about 15 or 20 years ago that shipbuilding is one of the most precise industries we have, because you really should be talking about things in parts per thousand or parts per million of accuracy. If I'm machining something a 1-inch diameter bar and I'm holding it to 1/1000th of an inch, which even I could do in the laboratory, okay, that's 1 part in 1,000. If I hold it to 5/10ths, which I may or may not be able to do that in the laboratory, okay, but a good machinist can hold 5/10,000ths. That's 1 part in 2,000 in terms of accuracy, precision. And you know, if you ever use vernier calipers, you know, or micrometers, that's kind of what you get in measuring things. However, has anyone ever seen a ball bearing micrometer? The types of micrometers they use to measure the balls on ball bearings, precision ball bearings. It's kept in an air-conditioned room, plus or minus 2 degrees Fahrenheit, and it's the size of a small lathe to measure something that might be 1/10 of an inch in diameter. But it measures it to 50 millionths. Because if you start thinking about coefficients of thermal expansion, 5 degrees Fahrenheit will change your dimensions, okay, by your tolerance. Holding something to 1/10,000th is 1 part in 10,000. Holding it to 50 millionths over 1 inch is 1 part in 20,000. And 1 part in 20,000. Holding it to 3 inches on one of those blocks is 1 part in 60,000. And it's pretty impressive. And now you're talking about a 1 or 2 degree temperature change will essentially wipe out your temperature differential, will wipe out your precision. Well, what type of precision do you have when you're trying to put 2 hulls together, 2 hull sections together, on a ship that's 100 yards long, and you're trying to fit up 1 centimeter thick or 3/8 of an inch thick plate to weld the hull, with the sun shining on one side and shade on the other side, right? You start looking at it, many times in shipbuilding, we're talking parts of precision of 1 part in 10,000, which is much more precise than they're holding on semiconductors and things like that, as a percentage of the distance they're working over. Because in ships, you're working over a huge distance. Now, you can use come-alongs and other things you can't use on a semiconductor, but nonetheless, you're introducing stresses, which they wouldn't dare do on the semiconductors. So it turns out you can argue that precision in shipbuilding is just as important or more important than it is in a lot of other industries, if you think about it in parts per million of temperature differential. However, getting back to our 2 types of adhesive bonding, something like a wetted liquid, if I have a piece of metal, like a windshield or a mirror for a windshield that goes on the windshield of my car, and I want to bond that to the glass has an extremely smooth surface. Even on an atomic scale, it's a relatively smooth surface, because the glass is just a liquid, and it cooled down and it doesn't have this rough surface. The metal might have a little bit of a rough surface, but that adhesive has to bond to the glass. So it either has to chemically react with the glass, or it actually has to work by this technique with a very, very flat surface, by type 1 adhesive bonding. However, most adhesive bonding is type 2 mechanical interlocking. And I actually have a little thing here. Kind of, well, actually, let's do some other adhesive bonding before we get there. But anyway, this is one type. You can see with Johansson blocks that bonds things together, but the most common is mechanical interlocking, where I just have things on a very fine scale, and the adhesive gets down between the pores. To get, well, actually, I can give you an example of it right now. One of the things that we do to improve adhesion is of things on aircraft. We will anodize the aluminum. Anybody know what an anodized surface looks like on aluminum in a microscope? It's very rough, and that's it. That's what the anodized surface looks like in a microscope, a scanning electron microscope. What you do with anodizing, and you can anodize this. If this is aluminum, it can be titanium. You can anodize niobium, a number of metals, tantalum. You pass an electric current, and you basically corrode the surface. If this is the anode, you will form an oxide. In this case, we'll call it aluminum oxide. If it's tantalum dioxide, or not dioxide, tantalum. For capacitors, let me back up. Let's say this is tantalum, Ta2O3. Most expensive tantalum, and I think I mentioned it before. It's one of the more expensive metals, about the price of silver. But it makes the best capacitors in the world. And the reason is you get a very high surface area when you grow the tantalum oxide. You're passing in a electrolyte, you're going to pass a current, and let's see, the anode current's going that way. The electrons are going that way. This is the, I'm sorry, no, the electrons are going this way. The electrons are going this way. This is the positive anode. The electrons are coming here, and they're basically corroding the surface. And you have to have spaces in between in the electrolyte where the oxide can go, or the electrons can go. Otherwise, this aluminum or this tantalum oxide are very, very good insulators. Okay, and so if they're insulators, if they were continuous across here, then you wouldn't be able to pass the electrons in the anodizing process. People have looked, and this is a model of the aluminum oxide surface, where you grow these cells of aluminum oxide. You have these channels in between where the electrons are flowing through this liquid electrolyte. And when you're all done, you end up with this very, on a microscopic scale, a very rough surface, which is great for mechanical interlocking. Now, it's not so good for corrosion. Anybody know what we do for anodizing to give it corrosion resistance? I mean, you have anodized aluminum on window frames and door frames, and you color it and everything else. When you grow the anodized aluminum, you'll have something like this, and this actually has the same crystal structure as corundum or sapphire. It's very strong. Tantalum is the best in terms of dielectric strength. It makes the best capacitors, and the reason it makes great capacitors is because it's got lots of surface area. And in fact, there's an article in the Boston Globe this morning about Joel Schindel over in electrical engineering. And he's trying to use carbon nanotubes to make great supercapacitors. Lots of surface area to store the charge, to get rid of batteries in your cell phones and everything else. You have a capacitor that can charge and discharge hundreds of thousands of times rather than 1,000 times like a lithium battery before it wears out. And you can charge it up not in hours but in seconds. Okay, just pump that current in there. You know, it'd be a great battery. Whether you can afford one or not is another story. But anyway, this is the very rough surface. But if I want corrosion resistance, I don't want something that's going to allow the electrons to get in here and keep the corrosion process going. So after I anodize something, I have to seal it, what's called sealing it. And sealing it means that you turn the current off, and typically the electrolyte you might use for anodizing aluminum might be sulfuric acid. You take it out of the sulfuric acid bath and you put it in boiling hot water. And in boiling hot water, you essentially corrode the rest of this and you fill up these things so it's not as porous. And so that gives you good corrosion resistance because now you have an aluminum oxide or kind of a corundum surface which has got better corrosion resistance than the thinner original native oxide down here. But you have to seal it. And sealing means you can also seal it by putting a polymer, basically painting. This makes a great surface for painting. Okay? You want a rough surface to get paint to adhere. My oldest son's Eagle Scout project was a bunch of railings, outdoor hand railings in a building. This is back in 1986 or 87. The building had been built in 85 and all the paint was coming off this galvanized steel 2 years later, just peeling off the great big sheets. They had done nothing to prep the surface of the zinc, the galvanized steel. Okay, they just painted it. And they put well, I don't know what they put, they just whatever they did. So for zinc, if you have a zinc surface, basically you use vinegar, or we use acetic acid because I can get it by the gallon here. Okay, and you grow a zinc acetate film on the surface, very porous layer on the surface. And so the first week we had the Eagle Scouts, the Scouts out there scraping the paint off, which you guys are familiar with having to do that, right? And at the end of the day, I gave all these. This was outdoor. These are outdoor things. You don't want Scouts painting indoors. And I gave them buckets of acetic acid mixed with water. So it's basically strong vinegar, and I had them just go paint everything. And what they were doing is they were roughening up the surface by forming zinc acetate. The next week we came back and we primed everything. Okay, we put a primer coat on, and then we put the final coat on. And now, 20 years later, some of that paint on those railings is worn away down to the zinc, but it hasn't come loose. Okay, it's adhered. Okay, because you got mechanical interlocking. Tremendous bonding. Same type of thing on aircraft. If you're going to do adhesive bonding, you want this type of structure, and you can either put the adhesive on here or you can put paint on here, and the stuff sticks. You can do it with tantalum if you're trying to paint tantalum. I don't know why you paint tantalum, but if you're trying to make a capacitor. If you don't, if you want corrosion resistance, you better seal it by filling it up with a paint or polymer, or you can grow the aluminum oxide in a by just boiling it in water for an hour or so, and the aluminum oxide will grow in between. I once had a problem. First time I ever went to Cape Cod, it was about 20 years ago, and a guy called me up, and it was winter, and he had bought himself a brand new boat, 40-foot long boat, cost him a fortune, I'm sure. And he was all upset because when he put it in the water at the end of the summer, he was getting corrosion all over the anodized aluminum. I don't know what you call the rail along the outer edge of the boat to keep it from falling in the water. I don't know if there's a name for that. Anyway, the rail. But this was all encased in mahogany, okay? And so to take that aluminum rail off with the mahogany at the surface there was going to cost a fortune. But it was corroding, and he had basically white rust, and he wanted me to go down as a metallurgist and look at his boat and tell him what had happened. And in fact, I went down and I looked at it and I said, well, whoever built your boat may have anodized it, but they didn't seal it, okay? They may have sent it out for anodizing, but if you don't ask for sealing, you're going to get lousy corrosion resistance. It'd be great for adhesive bonding. I mean, he could paint it at that point if he wants. I don't know what he did, but at least I told him what his problem was. So here's some, this kind of shows, over here shows how the stuff grows over time. It starts out like that, and it grows little fingers, and if you grow it to a thick enough layer, you get stuff like that. So that's the mechanical interlocking. Yep.
The oxide layer basically is what you showed us. It's like growing of those
Little fingers,
right? But then you said if that's the oxide layer creates that, and that's bad for corrosion. And then later on you said to prevent that, molten water, and it would.
Well, when you anodize, you're growing that oxide layer faster than you could ever do it in the real world. You're getting electrical energy to grow that oxide very rapidly. Ordinarily, that aluminum oxide will form a layer that's like 10 nanometers thick. And you want to grow something that's 1,000 times thicker. Well, you'd have to wait 1,000,000 years to have nature do it as the oxygen diffuses in. If I want to grow it fast, I can use electrical energy, which will change the kinetics of this thing, and I can grow that oxide layer, but in a very porous form, and I can grow it to a fraction of a millimeter thick. Okay, it might be actually about 1/10 of a millimeter thick, about 4 thousandths, is as thick as it gets. Does that answer your question? What?
Not really, but
Well, what's your question?
well, I guess you have this this growth of this oxide layer, which is great for mechanical heat, bonding, but it's
Right.
poor for corrosion. So one way to prevent that from or mitigate the corrosion effect on it was either to seal it, or I thought you said molten water, it would create a layer or something.
Boiling water is the sealing process. That's all sealing is. We call it sealing. You can either seal it by putting a polymer on there, which is basically painting it to fill up those pores, or you can boil it in water and the oxide grows together. Those honeycomb pores. In the boiling water, I'm letting natural oxidation occur in those pores, as opposed to trying to drive it electrically. I can get a thick layer electrically by doing it with electrons, but it leaves pores behind. If I just put it in boiling water, then I can fill up the pores. Okay, the water will essentially continue to oxidize it. Okay, so that's right. Okay, now another thing to talk about porous surfaces. After World War II, we learned how to cold form steel. And the key to learning to cold form steel happens to have been learning to phosphate the iron surface. So if I have another surface here that's iron, and I put it in phosphoric acid, I'll get an iron phosphate on the surface, which is very rough. I can also take chromates, and I can do it on aluminum surfaces. And I'll get, anybody ever seen a kind of a piece of aluminum that looks kind of yellowish? Or you ever seen a steel bolt? Looks sort of green yellow. A galvanized steel bolt with zinc. You can also zinc chromate. You don't always have to anodize where you use electric current. I can just get a chemical reaction with phosphoric acid on steel and form something porous, just like I showed you on the aluminum oxide, on the aluminum. I can just stick it in a chromate bath, aluminum or zinc, and I'll form a zinc chromate or an aluminum chromate on those surfaces. And those surfaces, I should have brought one, but if you've ever seen aircraft quality bolts, they often look sort of yellowish. They have a yellowish tinge to them. It's because they're chromated. And the chromate improves corrosion resistance. It's there for corrosion resistance in that case, but you also can chromate if you wanted for adhesion. And in fact, iron, where you put a phosphate on, people learned if you stick iron in phosphoric acid. What's the common form of phosphoric acid? What's the most common form you all know about, love, and drink? Coca-Cola. Okay? Coca-Cola's iron is not iron phosphate, it's phosphoric acid. Phosphoric acid is good for you. They used to get phosphates. They used to talk about getting a phosphate at the drugstore back 100 years ago. And in fact, that's where Coca-Cola came from. A guy had a drugstore and he was selling phosphates, and he started adding some cocaine to it and sold his Coca-Cola. And that's another story. You know why they call it 7-Up? Until 1931, 7-Up actually contained lithium. Anybody know what lithium is used for as a drug? Antidepressant. If you got bipolar disorder, go get some old 7-Up pre-1931, and that's where you get your lithium. Okay? It was an upper, and 7 is the atomic weight of lithium. So it's called 7-Up because 7 is the atomic weight of lithium, and it's an upper. Okay, it's an antidepressant. 1931 they took it out, but they kept the name. Okay, so Coca-Cola used to give you a little buzz. It had some, actually it wasn't cocaine, but it was came from the same root, the cocoa bean, and it basically wasn't refined cocaine, but gave you the same type of buzz. Not a 7-Up, different type of buzz. In any case, getting back to phosphoric acid and iron phosphate. After World War II, we learned that if you took steel and you gave it a phosphate coating, you would form something that would hold lubricants very well. And I told you that welding is the opposite of lubrication, and actually I can kind of feel it here a little bit. This is a piece of I thought it was all gone, but a cold form, this is the beginning piece of a just a piece of 3/8 inch rod that was sheared off, and it's the beginning part of making this part. If anyone's put some cheap wood furniture together at home, this actually happens to be a knurled piece that has threads on the inside. I'll pass it around. It's zinc plated now. Okay. To make this part, you start off with 3/8 inch rod. You shear it into a known length, and this was phosphated. You might feel a little bit of soapiness on the surface because they then use a stearate, basically a soap, as the lubricant. And what they wanted to do is they would first they just take this guy, which is a sheared end. This is all the pieces I got at a shop outside of Pittsburgh once. You might feel a little bit of lubricant on some of these, but they stamp it, cold form it in a die, and you'll see it's dished here, it's flat on the other end, and now it's sized to exactly the right size. The other one's just kind of rough cut. Then they start an extrusion process and start to make a little hole. So this one's a little taller than that one because they back extruded part way. And then they back extrude some more and make it even taller. And then they put a head on the end. And this one's still got a little hole in the bottom. And if you don't take this off, well, you can take it off a little bit. If you look inside, this is the only waste inside there. It's a little plug, a little steel plug. They punch out in the next operation. The next one, what have they done the next one? Oh, they changed and made a counter bore here by extrusion. Then they put the knurling on. Then they did the internal threads in the threading machine, and then they zinc plated it. And that's all the steps in making that little 2-cent part, or whatever it costs, okay? So you can pass that around. And the reason they were able to do that is they found that they tried to do it before, but there's so much metal sliding and deformation that without something to hold the lubricant there, they would get the steel welding to the dies in the cold forming operation. But with the iron phosphate and having places, little pockets on the surface here where you could have the soap lubricant stay for multiple operations, you could get good sliding all the way through making that part. Now that's a nice small little part. I've seen parts that go in the steering parts of your car that are, this size, the size of a softball or a grapefruit or something, that are cold formed. Almost no waste, formed extremely rapidly. You want to walk in those plants with earmuffs on because the machines are banging away. Well, they're actually banging away like that for small parts. I mean, several times a second. These great big machines slamming together with 1,000 tons of force, just taking steel and just cold forming it. Great properties because it's all cold work steel, high strength. You start with low strength material and end up with high strength properties. Lots of little widget parts with almost no waste, all because we learned to roughen up the surface to hold the lubricant. Okay, that was just after World War II. They also do this hot forming now, so they make even bigger parts. I had a student working at a plant where they make axles for General Motors and a few other people now, and they had big parts from the axles that were cold formed. I asked them to send them to me, but they didn't. I need to call them. But you pick them up, and there were layers of grease on there, soap that were, 1/10 of an inch thick. I mean, thicker than they should have been, where it just kind of caught in there. But basically, it's a soap lubricant, a zinc stearate type of lubricant. that allows you to do cold forming. Has nothing to do with welding, has the opposite of welding, but anyway, that's how it works. Any questions on that? So the next part of adhesive bonding, what I just told you was basically the two types, type 1 and type 2, where you can either have a wetted liquid between the two surfaces, and we don't have to get into gluons and gravity forces or any of that. In type 2, which is simple mechanical interlocking, which occurs in all kinds of processing that we do, and it's not just this guy with the sailboat. I can't even think of the other things, but I get people once a year coming to me with some sort of problem. The paint didn't stick, or we're gluing these things together and they're falling apart, and I say, well, what are you doing to roughen the surface? You know, and they say, what do you mean? And I say, well, no wonder. It's, you got a smooth surface, and your adhesive is really working by type 2 mechanical interlocking. You need to chromate it, you need to phosphate it, you need to anodize it, you need to do some type of surface conversion coating to prep the surface to make it rough, to get good type 2 mechanical interlocking. Now, type 1, in general, you don't want a rough surface. And I thought somewhere in here. I'll find it next time. Type 1, you want nice smooth surfaces where you can have that liquid in between, and you want to get those surfaces close together and have a very thin layer. If you do the homework problems, you'll get a chance to calculate some of those, and you can get some substantial forces. You'd be surprised at how big some of the forces are. You still have to have lots of bonded area. Now these two, or that one, I can quantify. This one is basically just how well those things stick together. And actually we can think about, well, no we can't yet, not yet. Let's go through some other things. That stuff is basically the thermodynamics of adhesion. If I want to go to the kinetics of adhesive joints, I have to look at something like this. And this is a problem that was solved by Stefan Boltzmann, or the Stefan Equation in physics. But he basically just looked at two flat plates with a liquid in between and said, okay, how much force does it take to squeeze the liquid between two plates? And it depends on the viscosity of that liquid. Okay, if it's a very viscous liquid, it's going to take more force to squeeze it together because you've got to shear the liquid and move it around as it flattens out. So if I want to know something about how thin a joint I can get to type 1, I need to solve the Stefan equation. And there's a book written by a professor of civil engineering here in 1961. It's out of print, and one of my students has borrowed it, so I can't bring it in and show it to you. But I'll never get it back. Anyway, he solves it. He solves a little differential equation. We're not going to go through and solve the differential equation. But the force time product here, and this is in chapter 16, or a version of this. To solve this equation of dynamically squeezing two things together, the force times the time times 3 times the viscosity times the velocity squared over 8 pi, and these are circular plates, is 1 over h2 to the 4th minus 1 over h1 to the 4th, where h is basically the initial distance of separation, or the distance of separation. So this is the initial, this is the final. Raised to the 4th power, you got viscosity in here, and you got a v squared. The formula that I actually gave you in the book, he goes through some other machinations, or in chapter 16, is the force time product. We're talking about a kinetic process, so we're worried about time. The force to squeeze these together times time is 3/4 pi viscosity A, which is the radius of the circular disc, 1 over h2 minus 1 over h1 squared. And this is all in chapter 16. That's the formula. So to get it thinner and thinner, I have to apply more force, because this is 1 over h2 squared. The a to the 4th, this is the velocity and stuff. This is just the area of that circular disc. But this is the final thickness. This is the initial thickness. if this is large, 1 over h squared goes to 0, then you can just take this, as he simplifies down here, as h2 squared with an a squared, whatever, okay? Pi a squared is the area of the circular disk, okay? And this little f, this is f is equal to pi a squared times little f. So one's a force and one's a pressure, so far as that goes. But the important thing about this equation, the force that you're squeezing things together and the time is dependent, mostly, this is just geometry, 3/4 pi a to the 4th, viscosity and the final joint thickness. So the strength of this joint goes as 1 over the final joint thickness, okay? So the thinner the joint, the stronger it's going to be. So how many of you have ever taken something that you put on the wall and it fell off the wall, and so you put it back on the wall, and what do you do with the adhesive? You just push it on harder, right? More pressure, right? You're just increasing the force-time product to get it to stay on there stronger. Okay? If I just put it on there lightly, it takes less force to take it off, right? But if I rub it on there, it takes a lot more force, right? As I'm getting essentially a thinner joint. Thinner joints are stronger joints than adhesive bonding. We can talk about other things about close-up notes tomorrow as far as that goes. You're squeezing out, this is the one I was looking for before, you're squeezing out some of those air bubbles and other things. For a smooth adherent, this is a smooth surface or a rough surface. This is good for mechanical interlocking. This is good for type 1 up here. And high pressures squeeze out the bubbles, make a thinner joint, which makes a stronger joint. Okay? Those are the two basic ways, but if I go back, 2 types of bonding, so those are my 2 themes today. But one of the things I also have here, I can make it thinner, and that goes as 1 over the thinness squared, or the thinness squared, okay? But the other thing in here that I can change is the viscosity. Now, some of you know some fluids. So if let's say I make a joint that's 10 times thinner, that'll make it 100 times stronger. And that turns out to be approximately correct. But what can I do to this viscosity? If I want to change viscosity, how much of a change, order of magnitude wise, can I get with viscosity? What's the viscosity? Anybody have any idea what the viscosity of water is? It's about 1 centipoise. Maybe 1.3, whatever, but it's about 1 centipoise. What's the viscosity of this table? The table has a viscosity. It's probably something on the order of 10 to the 18th. Okay? The highest viscosity ever measured was measured by Professor Orwan, the same guy who did this dislocation thing. He estimated the viscosity of the Finnish coastline, Finland, as 10 to the 22nd. And he was looking at geologic time scales. Because if I'm starting to look at a number that's 10 to the 22nd, my times need to be very long. I can't do it in the laboratory. I could actually put a load on a piece of metal or a wooden table and just put a load on, and just like silly putty, it would slowly deform if I put a big enough load on. And that measures the viscosity. Okay, if it's water, but the point here is liquids tend to have this viscosity between 1 and 10 to the 5th. We tend to think of things that are solid as having viscosities that are typically between 10 to the 10th and 10 to the 18th. If you start looking at a solid piece of metal. Lead might have a viscosity of 10 to the 14th or something like that. But lead, if you push on it for a long period of time, will creep. Okay? So we can talk about viscosities, and viscosity is just the resistance to shear. Okay? How much movement you get when you put a given shear strain on it. And like I said, Professor Orwan once measured or estimated the viscosity of the Finnish coastline is 10 to the 22nd. And none of us have time to wait around for that experiment. Well, if I want to make an adhesive joint, I can make it, I want to make it when the adhesive is nice and fluid. And then I'd like to get that adhesive to harden up and become solid. So if let's see, we don't have a beer bottle in here, but if you had a beer bottle, a lot of the labels aren't like these that wrap all the way around, but when those beer bottles are coming off the beer line, they're coming off at about 1 case a second. And they have to slap those labels on there and get them to adhesively bond to the glass in a fraction of a second, like a 1/10 of a second, which means the adhesive that bonds that label has to be very, very low viscosity. It has to flow like water in order to get a thin joint for the adhesive. And we'll go through some of these numbers tomorrow. If I had something that was like honey, the time it takes to bond the label to the bottle would slow down the whole beer line. Okay, you wouldn't want to do that, right? So, anyway, tomorrow we'll talk about how do you change the viscosity of things to make a joint quickly when it's low viscosity, but then switch it over to high viscosity. You can either read chapter 16 or you can think about it, guess about it, and we'll talk about it next.